Part 2, Chapter 11, Part 3 of A Popular History of Astronomy During the 19th Century. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Aaron Carlo in San Clemente, California. A Popular History of Astronomy During the 19th Century by Agnes Mary Clerke, Part 2, Chapter 11, Part 3, Recent Comets, Continued. A fifth member was added to the family in 1887. On the 18th of January in that year, Monsieur Thome discovered at Cordoba a comet reproducing with curious fidelity the lineaments of that observed in the same latitudes 7 years previously. The narrow ribbon of light contracting towards the sun and running outward from it to a distance of 35 degrees. The unsubstantial head a veiled nothingness as it appeared, since no distinct nucleus could be made out. The quick fading into invisibility were all accordant peculiarities, and they were confirmed by some rough calculations of its orbit, showing geometrical affinity to be no less unmistakable than physical likeness. The observations secured were indeed, from the nature of the apparition, neither numerous nor over-reliable, and the earliest of them dated from a week after perihelion, passed almost by a touch-and-go escape, January 11th. On January 27th, this mysterious object could barely be discerned telescopically at Cordoba. That it belonged to the series of southern comets can scarcely be doubted, but the inference that it was an actual return of the comet of 1880, improbable in itself, was negatived by its non-appearance in 1894. Meyer's incorporation with this extraordinary group of the ellipse comet of 1882 has been approved by Kreutz after searching examination. The idea of cometary systems was first suggested by Thomas Clausen in 1831. It was developed by the late M. Hoek, director of the Utrecht Observatory in 1865 and some following years. He found that in quite a considerable number of cases, the paths of 2 or 3 comets had a common point of intersection far out in space, indicating with much likelihood a community of origin. This consisted, according to his surmise, in the disruption of a parent mass during its sweep round the star latest visited. Be this as it may, the fact is undoubted that numerous comets fall into groups in which similar conditions of motion betray a pre-existing physical connection. Never before, however, had geometrical relationship been so notorious as between the comets now under consideration, and never before, in a comet still, it might be said, in the prime of life, had physical peculiarities tending to account for that affinity been so obvious as in the chief member of the group. Observation of a granular structure in cometary nuclei dates far back into the 17th century, when Cysatus and Hevelius described the central parts of the comets of 1618 and 1652, respectively, as made up of a congeries of minute stars. Analogous symptoms of a loose state of aggregation have of late been not unfrequently detected in telescopic comets, besides the instances of actual division offered by those connected with the names of Biela and Liais. The forces concerned in producing these effects seem to have been peculiarly energetic in the great comet of 1882. The segmentation of the nucleus was first noticed in the United States and at the Cape of Good Hope September 30th. It proceeded rapidly. At Kiel on October 5th and 7th, Professor Krüger perceived 2 centers of condensation. A definite and progressive separation into 3 masses was observed by Professor Holden, October 13th and 17th. A few days later, M. Temple found the head to consist of 4 lucid aggregations ranged nearly along the prolongation of the caudal axis, and Dr. Common, January 27, 1883, saw 5 nuclei in a line like pearls on a string. This remarkable character was preserved to the last moment of the comet's distinct visibility. It was a consequence, according to Dr. Kreutz, of violent interior action in the comet itself while close to the Sun. There were, however, other curious proofs of a disaggregative tendency in this body. On October 9th, Schmidt discovered at Athens a nebulous object 4 degrees southwest of the great comet, and traveling in the same direction. It remained visible for a few days, and from Oppenheim's and Hind's calculations, there can be little doubt that it was really the offspring by fission of the body it accompanied. This is rendered more probable by the unexampled spectacle offered October 14th to Professor Barnard, then of Nashville, Tennessee, of 6 or 8 distinct cometary masses within 6 degrees south by west of the comet's head, none of which reappeared on the next opportunity for a search. A week later, however, one similar object was discerned by Mr. W. R. Brooks in the opposite direction from the comet. Thus, space appeared to be strewn with the filmy debris of this beautiful but fragile structure all along the track of its retreat from the Sun. Its tail was only equaled, if it were equaled, in length by that of the comet of 1843. It extended in space to the vast distance of 200 millions of miles from the head. But so imperfectly were its proportions displayed to terrestrial observers that it at no time covered an arc of the sky of more than 30 degrees. This apparent extent was attained during a few days previous to September 25th by a faint, thin, rigid streak noticed only by a few observers, by Elkin at the Cape Observatory, Eddy at Grahamstown, and Cruls at Rio Janeiro. It diverged at a low angle from the denser curved train, and was produced, according to Brédikhine, by the action of a repulsive force 12 times as strong as the counterpull of gravity. It belonged, that is, to type 1, while the great bifurcate appendage, obvious to all eyes, corresponded to the lower rate of emission characteristic of type 2. This was remarkable for the perfect definiteness of its termination, for its strongly forked shape, and for its unusual permanence. Down to the end of January, 1883, its length, according to Schmidt's observations, was still 93 million miles, and a week later it remained visible to the naked eye without notable abridgment. Most singular of all was an anomalous extension of the appendage towards the Sun. During the greater part of October and November, a luminous tube or sheath of prodigious dimensions seemed to surround the head and project in a direction nearly opposite to that of the usual outpourings of attenuated matter. See Plate 3. Its diameter was computed by Schmidt to be, October 15th, no less than 4 million miles, and it was described by Cruls as a truncated cone of nebulosity, stretching 3 or 4 degrees sunwards. This and the entire anterior part of the comet were again surrounded by a thin but enormously voluminous paraboloidal envelope, observed by Schiaparelli for a full month from October 19th. There can be little doubt that these abnormal effluxes were consequence of the tremendous physical disturbance suffered at perihelion, and it is worth remembering that something analogous was observed in the comet of 1680, Newton's, also noted for its excessively close approach to the Sun, and possibly moving in a related orbit. The only plausible hypothesis as to the mode of their production is that of an opposite state of electrification in the particles composing the ordinary and extraordinary appendages. The spectrum of the great comet of 1882 was, in part, a repetition of that of its immediate predecessor, thus confirming the inference that the previously unexampled sodium blaze was in both a direct result of the intense solar action to which they were exposed. But the D line was, this time, not seen alone. At Dunecht, on the morning of September 18th, Drs. Copeland and J. G. Loza succeeded in identifying 6 brilliant rays in the green and yellow with as many prominent iron lines. A very significant addition to our knowledge of cometary constitution, and one which lent countenance to Brédikhine's assumption of various kinds of matter issuing from the nucleus with velocities inversely as their atomic weights. All the lines equally showed a slight displacement, indicating a recession from the earth of the radiating body at the rate of 37 to 46 miles a second. A similar observation made by M. Tholen at Nice on the same day gave emphatic sanction to the spectroscopic method of estimating movement in the line of sight. Before anything was yet known of the comet's path or velocity, he announced, from the position of the double sodium line alone, that at 3 p.m. on September 18th it was increasing its distance from our planet by from 61 to 76 kilometers per second. M. Bigourdan's subsequent calculations showed that its actual swiftness of recession was at that moment 73 kilometers. Changes in the inverse order to those seen in the spectrum of comet Wells soon became apparent. In the earlier body, carbon bands had died out with approach to perihelion and had been replaced by sodium emissions. In its successor, sodium emissions became weakened and disappeared with retreat from perihelion and found their substitute in carbon bands. Professor Rico was, in fact, able to infer from the sequence of prismatic phenomenon that the comet had already passed the sun, thus establishing a novel criterion for determining the position of a comet in its orbit by the varying quality of its radiations. Recapitulating what was learnt from the 5 conspicuous comets of 1880 to 82, we find that the leading facts acquired to science were these 3. First, that comets may be met with pursuing each other, after intervals of many years, in the same or nearly the same track, so that identity of orbit can no longer be regarded as a sure test of individual identity. Secondly, that at least the outer corona may be traversed by such bodies with perfect apparent impunity. Finally, that their chemical constitution is highly complex, and that they possess, in some cases at least, a metallic core resembling the meteoric masses which occasionally reach the Earth from planetary space. A group of 5 comets, including Halley's, own a sort of cliental dependence upon the planet Neptune. They travel out from the Sun just to about his distance from it, as if to pay homage to a powerful protector who gets the credit of their establishment as periodical visitors to the solar system. The second of these bodies to effect a looked-for return was a comet, the 16th within 10 years, discovered by Pons, July 20th, 1812, and found by Encke to revolve in an elliptic orbit with a period of nearly 71 years. It was not, however, until September 1st, 1883, that Mr. Brooks caught its reappearance. It passed perihelion January 25th and was last seen January 2nd, 1884. At its brightest, it had the appearance of a second-magnitude star, furnished with a poorly developed double tail, and was fairly conspicuous to the naked eye in southern Europe from December to March. One exceptional feature distinguished it. Its fluctuations in form and luminosity were unprecedented in rapidity and extent. On September 21st, Dr. Chandler observed it at Harvard as a very faint diffused nebulosity with slight central condensation. On the next night, there was found in its place a bright star of the 8th magnitude scarcely marked out by a bare trace of environing haze from the genuine stars it counterfeited. The change was attended by an 8-fold augmentation of light, and was proved by Schiaparelli's confirmatory observations to have been accomplished within a few hours. The stellar disguise was quickly cast aside. The comet appeared on September 23rd as a wide nebulous disk, and soon after faded down to its original dimness. Its distance from the Sun was then no less than 200 million miles, and its spectrum showed nothing unusual. These strange variations recurred slightly on October 15th, and with marked emphasis on January 1st, when they were witnessed with amazement and photometrically studied by Müller of Potsdam. The entire cycle this time was run through in less than 4 hours, the comet having, in that brief space, condensed with a vivid outburst of light into a seeming star, and the seeming star having expanded back again into a comet. Scarcely less transient, though not altogether similar, changes of aspect were noted by M. Perrotin, January 13 and 19, 1884. On the latter date, the continuous spectrum given by a reddish-yellow disk surrounding the true nucleus seemed intensified by bright knots corresponding to the rays of sodium. A comet discovered by Mr. Sauerthal at the Royal Observatory, Cape of Good Hope, February 19, 1888, distinguished itself by blazing up on May 19th to 4 or 5 times its normal brilliancy, at the same time throwing out from the head 2 lustrous lateral branches. These had, on June 1st, spread backward so as to join the tail, with an effect like the playing of a fountain. 10 or 11 days later, they had completely disappeared, leaving the comet in its former shape and insignificance. Its abrupt display of vitality occurred 2 full months after perihelion. On the morning of July 7, 1889, Mr. W. R. Brooks of Geneva, New York, eminent as a successful comet hunter, secured one of his customary trophies. The faint object in question was moving through the constellation Cetus, and turned out to be a member of Jupiter's numerous family of comets, revolving round the sun in a period of 7 years. Its past history came then, to a certain extent, within the scope of investigation, and proved to have been singularly eventful. Nor had the body escaped scatheless from the vicissitudes to which it had been exposed. Observing from Mount Hamilton, August 2nd and 5th, Professor Barnard noticed this comet, 1889 V, to be attended in its progress through space by 4 outriders. The 2 brighter companions, the fainter pair survived a very short time, were perfect miniatures, Professor Barnard tells us, of the larger comet, each having a small, fairly defined head and nucleus, with a faint hazy tail, the more distant one being the larger and less developed. The 3 comets were in a straight line, nearly east and west, their tails lying along this line. There was no connecting nebulosity between these objects, the tails of the 2 smaller not reaching each other or the large comet. To all appearance, they were absolutely independent comets. Nevertheless, Spittaler at Vienna in the early days of August perceived as it were a thin cocoon of nebulosity woven round the entire trio. One of them faded from view September 5th. The other actually outshone the original comet on August 31st, but was plainly of inferior vitality. It was last seen by Barnard on November 25th with the 36-inch refractor, while its primary afforded an observation for position with the 12-inch March 20th, 1890. A cause for the disruption it had presumably undergone had, before then, been plausibly assigned. The adventures of Lexell's comet have long served to exemplify the effects of Jupiter's despotic sway over such bodies. Although bright enough in 1770 to be seen with the naked eye, and ascertained to be circulating in 5½ years, it had never previously been seen, and failed subsequently to present itself. The explanation of this anomaly, suggested by Lexell, and fully confirmed by the analytical inquiries both of Laplace and Leverrier, was that a very close approach to Jupiter in 1767 had completely changed the character of its orbit, and brought it within the range of terrestrial observation, while in 1779, after having only twice traversed its new path, at its second return it was so circumstanced as to be invisible from the earth, it was, by a fresh encounter, diverted into one entirely different. Yet the possibility was not lost sight of that the great planet, by inverting its mode of action, might undo its own work and fling the comet once more into the inner part of the solar system. This possibility seemed to be realized by Chandler's identification of Brooks and Lexell's comet. An exceedingly close approach to Jupiter in 1886 had, he found reason to believe, produced such extensive alterations in the elements of its motion as to bring the errant body back to our neighborhood in 1889. But his inference, though ratified by Mr. Charles Lane Poor's preliminary calculations, proved dubious on closer inquiry, and was rendered wholly inadmissible by the circumstances attending the return of Brooks' comet in 1896. The companion objects watched by Barnard in 1889 had by that time, perhaps, become dissipated in space, for they were not redetected. They represented in all likelihood wreckage from a collision with Jupiter dating perhaps so far back as 1791, when Mr. Lane Poor found that one of the fateful meetings to which short-period comets are especially subject had taken place. The Lexell-Brooks case was almost duplicated by the resemblance to de Vico's lost comet of 1844 of one detected November 20th, 1894, by Edward, son of Lewis Swift. Schulhoff announced the identity, and Chandler, under reserve, vouched for it. Had the comet continued to pursue the track laboriously laid down for it at Boston, and shown itself at the due epoch in 1900, its individuality might have been considered assured. But the formidable vice-regent of the sun once more interposed, and, in 1897, swept it out of the terrestrial range of view. Hence, the recognition remains ambiguous. On the morning of March 7th, 1892, Professor Lewis Swift discovered the brightest comet that had been seen by northern observers since 1882. About the time of perihelion, which occurred on April 6, it was conspicuous as it crossed the celestial equator from Aquarius towards Pegasus, with a nucleus equal to the third magnitude star and a tail 20 degrees long. This tail was multiple, and multiple in a most curiously variable manner. It divided up into many thin nebulous streaks, the number and relative luster of which underwent rapid and marked changes. Their permanent record on Barnard's and W. H. Pickering's plates marked a noteworthy advance in cometary photography. Plate 4 reproduces two of the Lick pictures taken with a 6-inch camera on April 5th and 7th respectively, with, in each case, an exposure of about 1 hour. The tail is in the first composed of 3 main branches, the middle one having sprung out since the previous morning, and the branches are, in their turn, split up into finer rays, to the number of perhaps a dozen in all. In the second, a very different state of things is exhibited. The southern component, Professor Barnard remarked, which was the brightest on the 5th, had become diffused and fainter, while the middle tail was very bright and broad. Its southern side, which was the best defined, was wavy in numerous places, the tail appearing as if disturbing currents were flowing at right angles to it. At 42 degrees from the head, the tail made an abrupt bend towards the south, as if its current was deflected by some obstacle. In the densest portion of the tail, at the point of deflection, are a couple of dark holes, similar to those seen in some of the nebulae. The middle portion of the tail is brighter, and it looks like crumpled silk in places. Next morning, the southern was the prominent branch, and it was loaded at 1 degree 42 minutes from the head with a strange excrescence, suggesting the budding out of a fresh comet in that incongruous situation. Some of these changes, Professor Barnard thought, might possibly be explained by a rotation of the tail on an axis passing through the nucleus, and Pickering, who formed a similar opinion on independent grounds, assigned about 94 hours as the period of the gyrating movement. He, moreover, determined accelerative velocities outward from the sun of definite condensations in the tail, indicating for its materials, on Brédikhine's theory, a density less than 1/2 that of hydrogen. This conclusion applied also to Rodam's comet, which exhibited a year later phenomena analogous to those remarked in Swift's. Their photographic study led Professor Hussey to significant inferences as to the structure and rapid changes of cometary appendages. 7 comets were detected in 1892, and all, strange to say, were visible together towards the close of the year. Among them was a faint object, which unexpectedly left a trail on a plate exposed by Professor Barnard to the stars in Aquila on October 12th. This was the first comet actually discovered by photography, the Sohag comet having been simultaneously seen and pictured. It has a period of about 6 years. Holmes's comet is likewise periodical in rather less than 7 years. Its path, which is wholly comprised between the orbits of Mars and Jupiter, is less eccentric than that of any other known comet. Subsequently to its discovery on November 6th, it underwent some curious vicissitudes. At first bright and condensed, it expanded rapidly with increasing distance from the Sun, to which it had made its nearest approach on June 13th, until, by the middle of December, it was barely discernible with powerful telescopes as a feebly luminous mist on the face of the sky. But on January 6, 1893, observers in Europe and America were bewildered to find, as if substituted for it, a yellow star of the 7th magnitude, enveloped in a thin nebulous husk, which enclosed a faint miniature tail. This condensation and recovery of light lasted in its full intensity only a couple of days. The almost evanescent faintness of Holmes's comet at its next return accounted for its invisibility previous to 1892, when it was evidently in a state of peculiar excitement. Mr. Perrine was barely able, with the Lick 36-inch, to find the vague nebulous patch which occupied its predicted place on June 10th, 1899. The origin of comets has been long and eagerly inquired into, not altogether apart from the cheering guidance of ascertained facts. Sir William Herschel regarded them as fragments of nebulae, scattered debris of embryo worlds, and Laplace approved and adopted the idea. But there was a difficulty. No comet has yet been observed to travel in a decided hyperbola. The typical cometary orbit, apart from disturbance, is parabolic, that is to say, it is indistinguishable from an enormously long ellipse. But this circumstance could only be reconciled with the view that the bodies thus moving were causal visitors from outer space by making, as Laplace did, the tacit assumption that the solar system was at rest. His reasoning was, indeed, thereby completely vitiated, as Gauss pointed out in 1815, and the objections then urged were reiterated by Schiaparelli, who demonstrated in 1871 that a large preponderance of well-marked hyperbolic orbits should result if comets were picked up en route by a swiftly advancing sun. The fact that their native movement is practically parabolic shows it to have been wholly imparted from without. They passively obeyed the pull exerted upon them. In other words, their condition previous to being attracted by the sun was one very nearly of relative repose. They shared, accordingly, the movement of translation through space of the solar system. This significant conclusion had been indicated on other grounds as the upshot of researches undertaken independently by Carrington and Mohn in 1860, with a view to ascertaining the anticipated existence of a relationship between the general lie of the paths of comets and the direction of the sun's journey. It is tolerably obvious that if they wandered at haphazard through interstellar regions, their apparitions should markedly aggregate toward the vicinity of the constellation Lyra. That is to say, we should meet considerably more comets than would overtake us, for the very same reason that falling stars are more numerous after than before midnight. Moreover, the comets met by us should be, apparently, swifter moving objects than those coming up with us from behind, because, in the one case, our own real movement would be added to, in the other subtracted from theirs. But nothing of all this can be detected. Comets approach the sun indifferently from all quarters, and with velocities quite independent of direction. We conclude, then, that the cosmical current which bears the solar system towards its unknown goal carries also with it nebulous masses of undefined extent, and at an undefined remoteness, fragments detached from which, continually entering the sphere of the sun's attraction, flit across our skies under the form of comets. These are, however, almost certainly so far strangers to our system that they had no part in the long processes of development by which its present condition was attained. They are perhaps survivals of an earlier, and by us scarcely and dimly conceivable state of things, when the swirling chaos from which sun and planets were, by a supreme edict to emerge, had not as yet separately begun to be. End of Part 2, Chapter 11, Part 3, Recent Comets, continued. Recording by Aaron Carlo in San Clemente, California.